Okay, welcome everybody to this edition of the Spring Seminars. Today we are delighted to have Mark von Raamsdonk with us from UBC, and he's going to talk to us about Holo-ween. Over to you, Mark.
Okay, so thanks very much for the invitation to speak, and also thank you to everyone for getting up so early for my talk. And so I'm going to tell you a little bit of work, recently with my graduate student, Peter Simidza. This appeared in June, and I'll be explaining the title a little bit more soon. So this talk is motivated by this kind of deep connection that has been emerging between sort of quantum informational aspects of states in holographic CFTs and the dual spacetime geometries. The idea that the spacetime geometry might be more or less directly related to the entanglement structure of the quantum state. And so we have some explicit formulas like the Ryu-Takeyanagi formula that exhibits this relation. And it leads one to ask, how far does this go? How much information about the dual spacetime is really captured by these kind of what I call universal properties of the state? Universal in the sense that entanglement is something that you could look at in any quantum system. And I'm contrasting that with maybe more specific physics that would be specific to which CFT you're looking at. So we could ask, for example, does the internal space geometry, as well as the large dimensions, does that somehow have to do with entanglement structure of the quantum state or some analog of entanglement entropy? What about the matter fields in the space-time? Can these also be understood from some kind of quantum information perspective? So what I want to explore today is kind of an extreme possibility that maybe more or less everything is related to these universal features of the state, and that perhaps the precise microscopic degrees of freedom and the Hamiltonian for the specific CFT that we're dealing with are not so important. So one way to ask that question is to say, can we start with, say, a holographic CFT and some state that has a gravitational dual description? And then can we then look at another holographic CFT, one that we think maybe corresponds to a different theory of gravity? But by choosing the correct state in that second CFT, can we actually describe faithfully, encode faithfully, the original space-time that was encoded in the first CFT state? Okay, and this is the title. So of course, in Holo-ween, which I realize is more widely known in North America, people dress up as other things. So can we dress up the CFT2 to look like a state of CFT1 so that it still faithfully encodes the same dual geometry? So let me be a little bit more specific. So I want to think about a state of our holographic CFT1 at some particular time. And so we can ask, well, what is encoded in that state just at that one particular time? And so we often draw this picture to describe the dual asymptotically ADS spacetime dual to a state. If I just know the state, and maybe I don't know whether perhaps sources might be turned on in the Hamiltonian, then I can draw this region, this diamond-shaped region. It's the domain of dependence of a spatial slice, which ends at the time equals 0 slice on the boundary. And we could say that the usual understanding is that this particular state, in a sense, knows about this region of the dual space-time geometry. If I want to know about the rest of the geometry, I need to know what the CFT Hamiltonian is. So if I were to perturb that CFT Hamiltonian for my CFT1 at some time slightly after time equals 0, then that would actually have effects and change this state. And those effects would propagate into the space-time along some light cones. And similarly, if I were to change the Hamiltonian in the past, then I would affect this geometry outside of the diamond. So I want to think about just knowing the state at time equals 0 and not necessarily knowing the Hamiltonian for all possible times. This has information about this particular, what I'd call a causal diamond region or a domain of dependence region of the space-time. Okay. And so now the idea is we're going to look at a different, perhaps call holographic conformal field theory, CFT2. And I want to ask, can I find a state of CFT2 which encodes a dual space-time that includes some arbitrarily large region of this first space-time? Okay, so can I describe this red region using CFT2, even though the original space-time was described by some state of CFT1? Okay, so I want to start. So I think at first that sounds a little bit crazy. So I'll start with an obvious objection to this.
Can I ask?
Yeah, please ask lots of questions. Yeah.
So, like, I'm just trying to understand when is this even plausible, which is probably what you're going to talk about. But would you be assuming that you're looking at Largen theories, for example?
So
is Largen crucial to, like your...
Yeah, I mean, at first I want to have that in mind, that maybe CFT1 and CFT2 are both conventional holographic theories, but maybe dual to some different theories of gravity or naively different theories of gravity. By the end of the talk, I may relax this and think about whether what I'm saying might even be possible for CFT2s, which are not conventionally holographic.
Okay, so, for example, would you require CFT2 and CFT1 to have same central charge? Because
no. Yeah, no. So I'll specifically be considering different central charges.
Okay. So okay. So what about your and they differ by 1/n suppressed things, or even the leading in behavior is different? Or maybe, like if these questions are better answered.
Yeah, maybe hold off a little bit, because I think some of it will be more clear as I go.
Okay. Yeah, thanks.
All right, so one obvious objection. Oh, yes, please.
I think we have one more question.
Okay.
By Junik. Junik, maybe you can unmute yourself and ask your question.
Hello, sir. Am I audible now?
Yeah.
Oh, thank you. My question is actually a very basic kind of question, like the previous slide. Yeah, in this point where you explained, is it like we are trying to explain, we are trying to define one space-time curvature among the other, like hidden among the second time? Like we are trying to find the CFT2 whose dual spacetime includes inside the CFT1 spacetime dimensions or curvatures, like the structure.
Yeah, this is right. So CFT2 would maybe in the vacuum state encode some ADS, pure ADS spacetime, and I'll be asking, can I find some weird excited state of CFT2 where the spacetime inside actually is described by this other theory of gravity? But let me go on a little bit, and it'll be more clear why I would think that. Okay, so an obvious objection to this is that if I have, say, two different holographic CFTs, these things have different operators, spectra of light operators, and that would imply that the corresponding gravitational theories would have a different spectrum of light fields. So maybe both CFTs are dual to some gravitational theory, so we have a metric, but maybe we have different scalar fields in the two theories. Maybe we have different gauge fields in the two theories. And so given that, it seems hopeless at first to try to describe some space-time using CFT2, which has totally different fields than the gravitational theory that we think of as being dual to CFT2. Okay, so how could this possibly work? And So a key point here is going to be that these different theories of gravity, the thing that we think of as being dual to CFT1 and dual to CFT2. So while these are maybe, if we think more carefully, the semi-classical theory of gravity dual to CFT1 is just the theory that gives us a good description of the asymptotic regions of the space-time. And similarly, the semi-classical theory that we associate with CFT2 is the one that gives us a good description of the asymptotic regions of space-time dual to CFT2 states. But different semi-classical theories of gravity, these can be part of the same non-perturbative theory, as we've learned many times from string theory. And so we could actually have the following picture where our state of CFT2, which is maybe some high energy state, of course it has an asymptotic region, which is described by the usual semi-classical theory that we associate with CFT2. But it's possible that in the interior of the space-time, we could have some domain wall, some kind of stringy interface. And across this interface, the semi-classical theory that gives a good description might change. And so this is the idea that maybe we could find a state of CFT2 where outside of some bubble, then you have the semi-classical gravity theory number 2, but inside you have this other semi-classical gravity theory associated with CFT1. And then if that's true, then we could perhaps hope that the geometry and other fields inside the bubble could provide a good description, a good approximation to this interior region of our CFT1 dual. Okay, well, this is still a lot to ask, because now for this to work, we have to assume that CFT2 and CFT1 are dual to semi-classical theories of gravity that are part of the same non-perturbative theory. Okay, and I mean, at first it sounds impossible to know without knowing all about all of the non-perturbative theories of gravity and their different low energy descriptions. How could we possibly know whether these two theories of gravity are part of the same full non-perturbative theory? Okay, so I want to make a suggestion that this question is not as complicated as it sounds at first.
Oh, sorry, Mark, just a question.
Yeah.
So let's say, like I think of n equal to 4 superangles.
Yes.
With some SUN being the gate group. Then, like I can kind of, go to some, some part of the Coulomb branch or something such that I go to some SUN minus K.
Yes.
So would you say that these are an example of the CFT1 and CFT2?
Absolutely. So that would be a very simple example. You might ask, is it possible using SU 1000 to CFT n equals 4 super Yang mills to approximate part of a space-time which would be dual to SU 1001? And in this case, we know that the dual theories are part of the same non-perturbative theory, and we even know the physics of this interface. It's called a D3 brane. So you can see that in some string theory cases, it's very plausible that this can happen. But yeah, I want to argue that maybe it's even more generally true that these semi-classical theories dual to various holographic CFTs are going to be part of the same theory. Okay, so this is going to be kind of a key point here. So I want to suggest that theories of gravity that are dual to different CFTs should actually be part of the same non-perturbative theory, provided that these CFTs can be coupled non-trivially at some interface. Okay, so I've drawn the picture here. So provided that I could come up with a quantum field theory where on one side of an interface you have CFT1, on the other side of the interface you have CFT2, and these are coupled somehow so that energy and excitations could go from CFT1 to CFT2. Okay. So, this doesn't sound very hard. if you imagine these CFTs are descending from some lattice description, then you could imagine just describing your lattice theory on a lattice with some properties over here and some properties over here, and then the lattice fields at the interface interact with each other somehow. And then we would think that in the infrared, probably you end up with a theory where CFT1 and CFT2 interact across an interface. Okay, or if there's some UV quantum field theory description, we could just make the fields interact at the interface somehow. Okay. So it doesn't sound very hard. On the CFT side, let me now explain why I'm saying that this should imply the two semi-classical dual theories of gravity would be part of the same non-perturbative theory. Okay. And so basically the idea is just that if I can have an excitation in CFT1, and if later this excitation is seen in CFT2 because the excitation propagates from the original point across the interface to CFT2, if we think about what could the gravity interpretation of this be, well, we know that CFT1, this excitation corresponds to some excitation in the asymptotic region of the gravity theory dual to CFT1. And then the fact that you eventually see this thing as an excitation in CFT2 suggests that on the gravity side, in the asymptotic region of some space-time, which is dual to CFT2, now you see some gravitational waves or some other kind of gravity excitation. And so apparently, from the gravity perspective, you've had some excitation, some gravitational wave or something in this region, in one region of space. And then later you have excitations in another region of space, which is described by some other semi-classical theory of gravity. And so there should be some way that these are fitting together. There should be some way to describe this process on the gravity side. And so this suggests a picture like I've drawn on the right, where you have the two theories of gravity separated by some interface in the gravity theory. And in gravity, we expect that all of the geometry should be dynamical. And so instead of a rigid interface like we had in the CFT picture, this interface should correspond to some kind of dynamical brane. And that would be an object in the full non-perturbative theory. Okay, so to summarize, if I can couple these two CFTs non-trivially at an interface, just sort of in field theory, then this suggests that these two gravity theories should be coupled together. And in the gravity, the interface should be dynamical. And so we should think of that interface as being an object in a larger non-perturbative theory. Okay.
Sorry, Mark, again, just to go back to this three-brane example, an example of this would be cutting the three branes with the five branes. Would that be something?
Yeah, or just the previous example, if CFT2 could have super Yang-Mills with one gauge group, and CFT1 could be super Yang-Mills with a different rank gauge group. And then in that case, on the gravity side, we can have one cosmological constant and another cosmological constant, but really that has to do with some, in the full 10-dimensional picture, that has to do with some D3 brane flux. And then you just have some number of D3 branes here.
Yeah, I guess you can get that by just cutting it by five branes, then you can move the other D3 brane out, some number of D3 branes out on the left-hand side or something. Yep. Okay. But I can think of this example, right? No, that's
sure. Yeah, that's right. So I mean, okay, but I think the surprising thing here is, or to me, the surprising thing is, even if I didn't know about string theory and dualities and how all these gravitational theories are actually related to each other, I think this kind of simple argument, if you believe in holography, suggests that many of the semi-classical gravity theories that you would come up with, or the holographic ones, should actually be related to each other and part of the same theory. Just because it seems very, it's sort of surprising if I couldn't couple two CFTs together. I mean, maybe I can't do it for all possible pairs of CFTs, but it seems like a very kind of mundane thing to just be able to, you know, put two materials together and then have energy transfer from one to the other. It's harder to insulate them.
Thanks.
Okay. So now in this talk, I'm going to move on and just assume, so of course it's a very interesting question. I think this motivates understanding better whether it's possible to couple any two CFTs together. And, you know, if you could couple any two CFTs together, then this argument would suggest that there's just maybe only one non-perturbative theory of quantum gravity. But I don't want to go in that direction for this talk. I just want to assume that CFT1 and CFT2 are two holographic CFTs that can be coupled in this way. And now I'm going to ask the question, so given that their dual supergravity descriptions are part of the same non-perturbative theory, okay, then it's possible that this kind of picture could be realized. And I want to ask the question, what sort of state of CFT2 could I choose in order to have a dual that looks like this? So I want to give you a very explicit kind of construction. And the explicit construction of these states, it actually involves the interface theory that I was just describing. So let me describe this mapping from the Hilbert space of CFT1, say on a sphere, to the Hilbert space of CFT2 on a sphere. Okay. And so what I'll do is construct an operator that maps from this Hilbert space to this Hilbert space. And my operator will be constructed using a Euclidean path integral, which involves this interface theory. Okay. So the operator is called M, and it depends on a choice of interface, I. Okay, so I should say, given CFT1 and CFT2, there may be multiple ways for these things to couple across an interface. So given some choice of that, and given a choice of this parameter epsilon that I'll explain, then we will describe an operator. Okay, and so the operator can be described by its matrix elements. So if I have, so let's imagine that I have the matrix elements of this operator in a field space basis. Okay, so let's say I have some chosen fields of CFT1 on a sphere, and then some chosen fields of CFT2 on a sphere, and I want to evaluate the matrix element sort of phi2 m and then phi1. Okay, and so then this is defined by doing a path integral. So now we think about this this interface theory on a cylinder, and I choose boundary conditions where the fields at the bottom are these fields phi1 in the matrix in the state on the right, and I choose fields phi2 to be those of the state on the left. Okay, and then I just integrate over all the configurations in this interface CFT. So I'm integrating over, you know, the CFT1 configurations and the CFT2 configurations, and then these sort of meet at the interface. Sometimes we even have additional degrees of freedom living at the interface, and then we would integrate over those as well. Okay, so this Euclidean path integral, then it gives us a definition of this operator. Okay. So this is very similar to how I would you know, describe, say, the thermal density matrix. If I didn't have an interface here and I just had CFT1, then this path integral would be the path integral that describes the thermal density matrix operator, or the density operator for CFT1. Okay. All right. So now I want to interpret this operator in terms of some quantum mechanics picture, some Lorentzian picture. And so what it is you can think of starting with some state of CFT1, and then this bottom part here would correspond to some Euclidean evolution with Euclidean time epsilon1 with the CFT1 Hamiltonian. The interface is the place where we're kind of changing our theory from CFT1 to CFT2, And so from the quantum mechanics picture, we would call this a quench. So given any interface, there would be some associated quench operator that takes our state of CFT1, and now it spits out a state of CFT2. Okay, so we've changed the Hamiltonian. Now, after I do that, I'm likely to have a state with an infinite energy. So if I have two different quantum field theories, the UV structure of finite energy states of these two different theories is generally going to be different. And so if I simply take a state of CFT1 and interpret it as a state of CFT2, it's likely to have kind of the wrong UV structure to give me finite energy. And so the role of this, this final piece of Euclidean evolution with respect to CFT2 Hamiltonian will be to smooth out those infinities. So this operator, this a little bit of Euclidean evolution, which is described by the Euclidean time parameter epsilon, that will end up giving us a finite energy state of CFT2. Okay, so this is the operator. In the end, we're going to take epsilon 1 to 0 because that original Euclidean evolution isn't necessary to provide a finite energy state. Okay.
Sorry, Mark, a quick question.
Yeah.
Could we construct explicit examples of this Q operator if these CFTs were, let's say, minimal models? Are there examples of this Q? Okay.
Yeah. So let me describe a little bit more about these interfaces and how they would be classified, and I'll say a little bit about specific examples. Okay. So one way, so how do we think about these interface operators, or in general the interfaces between CFT1 and CFT2? Okay. So a nice way to think about it is by what's known as the folding trick. And so we think of an interface between CFT1 and CFT2 as actually a boundary condition for the tensor product theory. So we can think of a tensor product theory between CFT1 and a CFT, which is the mirror image of CFT2. It's maybe it's the same CFT. So you can imagine starting with this tensor product theory, and then asking, what are the possible boundary conditions for that tensor product theory? Okay, and some of the boundary conditions are trivial. They just correspond to choosing a boundary condition for CFT1 and then a boundary condition for CFT2. And then you just have these two theories that don't interact. But there can be other boundary conditions for the tensor product theory through which the two CFTs interact. Okay. So in the folded picture, the interface corresponds to a particular kind of boundary condition for the tensor product theory through which these things interact. And now once we've expressed this thing as a particular boundary condition for some CFT, then we have sort of an in-principle way of classifying the different interfaces. So just like there's a bootstrap for CFTs that might in principle determine which CFTs are possible, there's some similar bootstrap that would in principle determine which boundary conditions are allowed for a given CFT. Okay. So in general, this is a difficult problem, but it's possible to solve it, at least in some very simple cases. If you take, for example, both of these CFTs, if you took each of those to be the Ising CFT, then all of the possible boundary conditions are classified. So in that case, you have the same CFT on both sides. But I think there are some results with other minimal models. I don't think there's a full classification in the case of sort of two general minimal models, though.
Thanks.
Okay. Okay, so in the end, I won't need to think too much about these microscopic details, but I will mention one very important parameter that'll come up in our story. Okay, so just like the CFTs themselves usually have some parameter that is one or more parameters that is related to the number of degrees of freedom of the CFT. So in 1+1 dimensions, the central charge, or in higher dimensions, we have some kind of corresponding parameters. There's also a parameter, again, with different names depending on the dimension, there's a parameter that would relate to the number of degrees of freedom associated with this interface. Okay, or to the, in 1+1 dimension, this parameter is called the interface entropy. And the reason is that in 1+1 dimensions, we can look at the entanglement entropy. So suppose we have an interface theory with some interface. And now suppose we look at the entanglement entropy in the vacuum state of that theory of an interval that stretches a distance L on either side of the interface. Then the entanglement entropy has a universal form. And this includes a bulk term, which depends on the central charges on the two sides. And in addition, there is a finite contribution here, which is generally different depending on which interface you choose. And so this finite contribution to the entanglement entropy of this interval is what we call the interface entropy. So that will be an important parameter for us. I think you should think of it as being related to, say, the number of degrees of freedom associated with the interface, just like the central charge is associated with a number of bulk degrees of freedom. Okay. So in this talk, I want to mostly focus on the case where we're looking at the vacuum state of CFT1. And so we choose CFT2, and then we apply this operator to the vacuum state of CFT1, and that gives us our state of CFT2. This is the state that I'm going to claim or that I'm going to investigate whether or not it gives a good description of the original gravity dual. Okay. So if I sort of apply this operator on top of the vacuum state, okay, so we remember that the vacuum state, I can get starting with any state and then just doing an infinite amount of Euclidean evolution. So in terms of a Euclidean path integral diagram, that's sort of this bottom part. We have a semi-infinite cylinder here, and then we have the operator. So that involves putting an interface and putting a little bit of Euclidean evolution with respect to the CFT2 Hamiltonian. Okay, so this is the definition of my state psi 2 of CFT2. It's the path integral in a Euclidean interface CFT with this geometry where the wave functional evaluated on some specific field configuration would be this path integral with boundary conditions that the CFT2 fields on this top sphere have to be that field configuration. Okay, so this is the state I will consider. Once I choose the interface and I choose my parameter epsilon, then this state is completely specified. And we can ask, what is the dual geometry of this state? Okay, so now we can sort of apply, because this is a state which is constructed using a Euclidean path integral, then we can actually apply a standard kind of ADS CFT recipe to figure out what the dual geometry is. And so I'll just remind you a little bit about that. So if I wanted to take my state and evaluate some observables, some matrix elements, what I would do is I would take this part, the path integral that defines the state, and then a corresponding path integral that defines the bra of that state. And so that the full path integral would look like this. And then maybe I would, if I'm interested in operators at time equals 0, I would insert some operators at this central slice at time equals 0 in CFT2. And that's how I would do the calculation in CFT. Because these are holographic theories, then there's going to be some dual gravity calculation I can do instead. And so this gravity path integral, this CFT path integral would be associated with a gravity path integral where this picture kind of sets the boundary conditions. Okay. And so the dual geometry that we're looking for, so that the gravity path integral we assume is going to be dominated by some saddle point, and that saddle point geometry is going to have some asymptotic regions that would be described by this theory dual to CFT1. Sorry, this should say 1 and this should say 2. So the asymptotic regions close to this boundary would be described by the semi-classical theory associated with CFT1. The asymptotic regions near this strip of the boundary would be described by the other gravity theory. And then on the bottom, again, the asymptotic region near this boundary would be described by the first gravity theory. And between these two gravity theories, there should be one of these interface branes. Okay. And if you think about it, there's really two simple topologies that are likely to appear. One of them has a disconnected pair of interface branes, and the other one has a single connected interface brane. And we'll need to evaluate which of these has the least action. So for the story that I want to tell, it's the right-hand configuration that we were hoping for. Okay. So starting from these Euclidean geometries, how do I think about the actual Lorentzian geometry that would be dual to the state psi 2? So the recipe is that, well, here we have a time reflection symmetry. And in these cases, the initial data for the Lorentzian geometry is obtained simply by slicing the Euclidean geometry at the time symmetric slice. And then the geometry of that slice and any field configurations on that slice would be the initial data for our Lorentzian problem. So let's look at these slices. The slices are indicated in blue here. So you see in the first case, the time equals 0 slice, it's entirely described by gravity theory 2. Okay. And so this is not what we hoped for. But in the second case, if it happens that this is the right Euclidean solution, we see that the time equals 0 slice has an asymptotic region described by gravity theory 2, but an interior region described by gravity theory 1. And that's just like what I drew in the picture early on. So what we want to do is investigate in the context of some kind of calculable holographic model, when does this second kind of geometry dominate? And when does the first kind of geometry dominate? Okay, so we need to work with a holographic model. We need to understand on the gravity side, what are we going to use for the bulk action? How are we going to describe this interface brane? Okay, and here we kind of move away from a microscopic approach to more of a bottom-up approach to doing ADS CFT. Okay, so before I do that, let me just comment a little bit more about the interface brane. So I mentioned that this thing could be a brane of string theory. I just wanted to mention another possibility is that this kind of brane could really be a smooth object in the full 10-dimensional picture. This brane could be sort of a region of space-time where the internal space makes some transition from one configuration to a different configuration. And there are actually microscopic solutions of this sort known. So someone earlier mentioned the quantum field theories that you get by thinking about D3 branes ending on various kinds of D5 branes. So you can have n equals 2 or sort of half supersymmetric quantum field theories that correspond to n equals 4 on either side of an interface. And then there are various possible kinds of interfaces associated with which types of and which number of 5 branes you have in between. Okay. And in these models, you actually understand very well what are the gravity duals, because you can find all of the solutions of type 2b string theory with the corresponding, or of type 2b supergravity with the corresponding symmetries. Okay. And these things realize the feature I just mentioned. Okay, so these microscopic duals, the microscopic version of this picture on the right could be some smooth 10D geometry where there's not an actual brane, or you can think of there being some branes, but there's a lot of them and they've turned into geometry. Okay, but for this talk and our paper, we're going to take a bottom-up approach to studying our question. And so we'll simply assume that each of the CFTs is dual to some gravitational theory, we allow for the possibility of different central charges. And so on the gravity side, this will correspond to having different possible cosmological constants on either side. And then we'll just describe the interface brane in the simplest possible way by specifying a tension parameter. So like a brane cosmological constant. This is the simplest kind of action we could write down for the brane, just the integral of some constant times the square root of the determinant of the induced metric. Okay. So of course, in a microscopic model, things will be more complicated, but this is sort of the simplest thing we could look at in the bottom-up approach. I'm also going to focus for this talk mostly in on the case of 1+1 dimensional CFTs, so where we're talking about 3D gravity, again, because this is kind of the simplest thing that I can do. Okay, so I just said that. Let's move on. Okay, so let me describe, using this simple model, I'll describe the gravity dual of a very simple configuration before we get on to describing ultimately we want to describe the gravity dual of this sort of configuration. But let's warm up a little bit by considering just this configuration, the vacuum state of the interface CFT, where I have parameters C1 here and C2 here for the central charges, and then some interface entropy describing the interface. And so what you find is that the dual gravity solution, you can think of it as taking a patch of Poincare ADS. So in this case, I'm just assuming that the interface, as I said, it has a tension. You know, in general, it could couple to scalar fields and other things, but I'm assuming it doesn't, so that my entire solution is purely gravitational. In 3 dimensions, then the bulk geometries are locally ADS3. And the solution that I would have, given the 2 cosmological constants and the tension, would correspond to just some portion of that ADS3 on the left with 1 cosmological constant kind of glued on to a portion of the ADS3 on the right with a different cosmological constant. And so that's indicated in the picture. And these angles, which are in Poincare coordinates, they would be determined by the 2 cosmological constants and the interface tension. Okay. One reason to look at this this picture is that we will learn that this interface entropy is actually directly related to the tension here. Okay. So that will be important for us. So let me make that relation. Yes, please.
Hi, Mark. Sorry, can you hear?
Yeah, I hear you, Shiraz.
Yeah. If the two CFTs have the same central charge, then it's just the solution is just pure ADS.
So if the 2 CFTs have the same central charge, we can still have a non-trivial defect, and there can be a defect entropy, and then the 2 angles would be the same, but they don't have to be 90 degrees. So if this G parameter, or if this log G parameter is 0, then we'll see that interface has 0 tension, and then it's basically just ADS3. But in general, we can have an interface which is non-trivial, that has an interface entropy, and then you can have say, you know, theta here and the same angle there, and you sort of glue the space-time along the interface. But there's kind of an excess angle if you take the angle from here all the way to here.
Wait, my internet went in the middle. I couldn't quite hear your answer. Please move on. I'll ask you at the end.
Okay. Yeah. Okay. Sorry. Okay. So let's consider this the definition again of this boundary entropy parameter. Okay. And so this was the entanglement entropy of some interval with length L on either side of the interface. And now we can relate that to properties of our gravitational solution by using the Ryutaki-Yanagi formula. Okay. So we we take, as usual, sort of the minimal area surface in this space-time, which is now this part glued onto this part. Okay. And so the surface is some curve, some extremal curve, which will end, I mean, it'll pass through the interface somewhere. So we have to kind of allow that place to vary, and we allow the shape of the curve to vary. And then we find the extremal area surface going from here to here, and we calculate the area. And geometrically, it turns out that the log G part, so that was one part of our entanglement entropy, that corresponds exactly to this part that's shaded of the RT surface. Okay. So these parts here correspond to what I called the bulk contributions to the entanglement entropy, and then the remainder, which is log G, corresponds to this area plus this area. Okay. So an essential point is that the higher the tension of my interface, the larger these angles end up being. And so the thing that we want to take away here is that there's a direct relation between the interface entropy and the tension of this interface brane in the gravity picture. Okay. And in particular, you find that some finite interval of brane tension, so this particular interval maps to the full space of possibilities for this interface entropy. Okay, so now we're ready to attack the full problem. So remember, we had this particular CFT path integral that we would use to compute properties of my approximated state. And I want to understand what is the gravity dual of this CFT, of this interface CFT on the cylinder. And so as advertised earlier, we have sort of two possible types of solutions. And what I've drawn on the right, so now I'm kind of suppressing the angular direction around the cylinder. So the dotted line is the center axis of this cylinder. And so now we have these two possibilities where in the first possibility, we see these two disconnected pieces of our interface brane. This is the one where the time equals 0 slice is completely described by the gravitational theory dual to CFT2. Okay, so we can find solutions of this type, but then we also have solutions of the other type. Okay, so the other type is what we wanted, where you have a portion of the vacuum ADS solution corresponding to CFT1, okay, but that actually covers the entire central axis. And the interface has this geometry. So this is the inside of our solution, and then this is glued on to a portion of it turns out you need to consider the ADS Schwarzschild solution. Okay, so the whole setup here is spherically symmetric. So because we're doing ADS, because we're doing 3D gravity, we're assuming that the branes don't couple to any scalar fields, then the bulk geometries are just pure ADS, and generally, even in higher dimensions, they would be ADS Schwarzschild. Okay, so this is sort of the general story. We can either have this one with just slices of pure ADS glued to each other, or we could have this one where we have an interior with pure ADS glued to an exterior, which is ADS Schwarzschild. Maybe I'm just going to flash so here's a 3D picture. I think it's a little bit easier to see in the 3D picture. So what I'm saying is that in this band outside here, then you would have some ADS Schwarzschild mass parameter. Okay, so the interface itself has some tension. You would see that in the exterior geometry. Okay, so we just calculate. We find all of the possible solutions. where we're going to fix the cosmological constants, L1 and L2. We fix the brane tension, and then we fix this parameter epsilon that was a property of our state. And remember, what we want to do is actually think about the case where epsilon is very small. Okay. So we do this, we start with a CFT1 state, we do this quench that changes the Hamiltonian to the Hamiltonian of CFT2, and then we have a little bit of Euclidean evolution to smooth things out and give us a finite energy state. But in some sense, we want as little Euclidean evolution as possible because we don't want to, we sort of want to preserve the entanglement structure. We want to preserve the quantum information properties of the state as much as possible. Okay. So we have small epsilon, we have two cosmological constants, we have kappa. We find all the allowed solutions. Sometimes there's more than one solution. Sometimes we have a solution of each type, and then we have to compare the actions for the various solutions. Okay, so just like in analyzing the Hawking-Page transition. Okay, so I'll skip all of the details and then jump to this phase diagram. So let me explain the phase diagram. So what I'm doing is plotting on the horizontal axis the ratio between the two central charges, or between the cosmological constants. Okay. So in this direction, this is the point where both CFTs have the same central charge. Here, the CFT that we're using to approximate CFT1 has more degrees of freedom. And then on the other side, the CFT has less degrees of freedom. The vertical axis is this boundary entropy. And remember that had some finite interval of values that maps to all of the possible values of log G. So this bottom pair of line segments corresponds to log G equals minus infinity. The top one corresponds to log G equals plus infinity. Okay, so the important thing is whether we're in the pink region or in the other regions. What we wanted was to be in the other regions where the least action solution has a bubble, and then inside the bubble, we would have the geometry dual to CFT1. Okay. So that seems to be the case always if CFT2 has more degrees of freedom than CFT1. Okay, so if we're trying to approximate a state of a holographic CFT with a different holographic CFT that's sort of more complicated, that has more degrees of freedom, then when we construct our state, it seems to work all of the time. Okay. On the other hand, if the CFT that we're using to approximate the original one has less degrees of freedom, then, well, at least in some interval, if CFT2 has a central charge which is larger than 1/3 of the central charge of CFT1, then provided that this interface entropy is large enough, we still get the bubble geometry having the least action. Okay, so we still seem to be able to have a bubble that has the dual of CFT1 inside.
So, sorry, Mark.
Yeah.
So should I worry about something like C theorem here? I mean, like, does it constrain what possibilities I can have, or? Yeah.
So what I'm talking about here is not an RG flow. Right. So here I'm talking about it's sort of similar in that, we have some behavior towards the boundary and some behavior in the interior. But here what I have is some excited state of CFT2. And so, we're not really getting an RG flow to a theory with a higher central charge. It's just that we have we have some kind of a bubble inside the geometry, where inside the bubble you are approximating a gravity theory associated with a CFT that has higher central charge. So I think the C theorem doesn't give you any no-go theorems in this case.
But if we're just talking about ground states or something, I'm just wondering whether there should be at least some limit where you should see something like C theorem, right? Or is that, am I being wrong?
Well, I mean, of course, the C theorem would govern what you could possibly get if you turned on. So if you deformed your theory by a relevant operator, a relevant, so you take your CFT1, you turn on a relevant operator, and then you look at what is the IR theory. So of course that IR theory is constrained by this C theorem. Here I'm doing something quite different. I'm just taking the original unperturbed theory, and I'm looking at a state which might be a very high energy state. And I mean, in fact, this is, I think, the way that you can think of getting around the maybe counterintuitive. So the fact that you could approximate the vacuum of one CFT with a CFT that has fewer degrees of freedom is a little bit counterintuitive. But if I think of a very high energy state of that second CFT, then the number of effective degrees of freedom can be large. So I sort of liberate degrees of freedom by adding energy. And the idea is by adding enough energy, I can actually come up with a state of CFT1, or sorry, of CFT2, which gives a good approximation, at least to a finite volume of this original geometry.
So a related question. So these kind of the interfaces that we have, like, are you imposing some kind of energy conditions on them, like some, like should they tend to be positive, or are you allowed to? Yeah.
So I mentioned that the tension. So the kappa is the tension parameter. It turns out this is always positive, even for a negative boundary entropy. This kappa parameter is always positive. And that seems to be, so that's basically saying that this object is a positive energy interface. We don't need to consider negative energy interfaces, even if we're talking about negative boundary entropies.
Okay.
Okay. So I'm going to come back to this question of what happens for C2 less than 1/3 of C1. Let me just give you a Lorentzian picture. So, I promised that we could take our CFT path integral, go to the gravity path integral, look at the solution that's a saddle point, and then we're going to slice it and use that slice as the initial data for the Lorentzian solution. So what do these Lorentzian solutions look like in the left-hand region? This is the region that we like, where we have a bubble. So I'm going to explain the difference between the orange and the blue. And so that's simply what a qualitative difference in the exterior of the spacetime. So these spacetimes have an inside of the bubble, which looks like vacuum ADS, and then the bubble eventually collapses on you. Okay, so remember, my goal was just to approximate a sort of causal diamond region of the original geometry, and so this does that in either case. The difference between the two cases is that sometimes, so if you look at the spacetime from the exterior, then in one case, you have a bubble which collapses into a black hole. And in the other case, you have a bubble which is already behind the horizon of a black hole. Okay, so in this second case, the exterior geometry is just always Schwarzschild. Okay, so the summary so far is that we started with a vacuum of CFT1. We defined this particular state of CFT2 using a Euclidean path integral involving some interface CFT. And we argued that in our simple holographic model for dealing with these interface theories, that this state faithfully encodes a bubble of the geometry dual to CFT1, as long as either CFT2 is greater than CFT1, or sorry, central charge 2 is greater than central charge 1, if we have more degrees of freedom, or even if we have less degrees of freedom in some interval, and the boundary entropy parameter is large enough. Okay. But now actually I'm going to argue that even if C2 is even smaller, so maybe C2 is 1/10 of C1, so far the state that we've constructed doesn't seem to do a good job approximating the original vacuum state. But maybe that's because we tried to do too big of a jump from a theory with one central charge to a theory with a much smaller central charge. We could consider a more general thing where you actually try to do the approximation in steps. And so what I can imagine is starting with CFT1, and then instead of trying to jump directly to CFT2, I include a number of layers, so I include a complicated interface where in each layer I take a CFT and have an interface with a CFT that has some like somewhat smaller central charge, maybe half or 0.9 or 0.99 if I want to do things very gradually. Okay, so I could make a series of steps where I approximate the vacuum state of CFT2 with some state of CFTn. Okay. Then I approximate that state of CFTn with some state of CFTn minus 1, using the same kind of operator that we've been talking about. And I just repeat this. So, if you believe that I can approximate a state of one CFT with a state of another CFT that has a slightly smaller central charge, well, then I just repeat that a bunch of times, and eventually I've approximated the initial state with a state of a CFT with maybe a significantly smaller central charge. Okay. And so we've investigated this. Again, you have to look at the various possible gravity solutions, the various possible topologies of these interface branes. And actually now this is, since the talk, I could take out the word preliminary. Within the context of our simple holographic model, we found that it is possible to find a choice of these parameters epsilon and a choice of the intermediate central charges so that this works, so that the dominant solution actually ends up having a bubble of the gravity theory dual to CFT1 sort of nested inside a bunch of other bubbles. Okay, so again, in the context of this very simple holographic model, we found that any CFT, regardless of what the central charge is, we can make some choice of the interface entropy and some choice of the state so that our chosen CFT2 can encode a bubble of the spacetime dual to the vacuum of CFT1. Okay, and the size of this bubble, yeah.
So can I reduce the C2 to 0?
Yeah, so within the context of our model, there seems to be no restriction on how small I can make C2. I just need more steps. Okay. Now, of course, we're assuming that this model, this is a bottom-up model, so we're assuming that some classical gravitational equations provide a good description, and so of course we don't really think that's going to be true in general if C2 is once C2 becomes very small. But I think it's interesting that in the context of the model, there doesn't seem to be a lower bound on C2. I mean, we could have found that for C2 half as big as C1, you just can't do it even within the context of the model. But I find it very interesting that within the context of our model, there seems to be no lower bound on C2. So it kind of suggests that even if CFT2 is much simpler than CFT1, by looking at a very complicated state with high energy of CFT2, we can actually find something that approximates well a bubble of CFT1. So maybe that suggests that, if you extrapolate that to sort of microscopic models, maybe it suggests that even non-holographic CFTs, if you put them in the right state, they could still kind of encode geometry. So maybe any CFT could be holographic, but of course we can't conclude that from this model. Okay, I'm nearly done. I actually have no clock at all, so I'm probably over time, but I'll finish soon. So I'll just mention, we've focused on approximating the vacuum state of CFT1 with CFT2. But exactly the same operator I defined, well, that just gave us a map from the Hilbert space of CFT1 to the Hilbert space of CFT2. So we could apply the same mapping to any other excited state. And a nice class of excited states where we can understand the duals explicitly are those that we define by starting with the path integral that describes the vacuum state of CFT1 and adding some sources for various light operators. Okay, now, so these these states would have a geometrical description, and then you just do the same thing. One could figure out what the gravity dual is in this case, and it'll just be like this the set of geometries that we looked at before, but now with some perturbations. So exactly the same mapping that we used for the vacuum state should work for these excited states. Even for very highly excited states, if we started with, say, a thermal state of CFT1 that maybe is purified by another copy of CFT1, well, I can approximate that thermal state again by acting with the operator that I defined, this M operator. I act with that on the CFT on the right side, and I don't do anything to the left side, and that will give me some entangled state of CFT1 and CFT2. Okay, and so then my black hole geometry, which would be dual to the thermal field double, that will be approximated by some kind of black hole geometry where the asymptotic region again is described by the gravity theory dual to CFT2, but then we'll have a bubble, and then inside the bubble will be this black hole that was dual to our thermal state of CFT1. Okay, so my student Peter is investigating this this situation in more detail. This is just a picture of the spatial slice of our Lorentzian theory. Okay, so let me summarize. So we've done some calculations with a simple holographic model. They motivate, but certainly don't prove the following statements, but I'll try to present the general picture that might be true. So first we suggested that if I have two CFTs that can be coupled non-trivially at an interface, then the corresponding theories of gravity, if these are holographic, should be part of the same non-perturbative theory. Okay, so that suggests that, instead of different CFTs as being dual to completely different gravity theories, there really just would be dual to different low energy descriptions, different semi-classical theories of gravity that might be part of the same full complete theory. An interesting question that I didn't pursue is whether there is more than one class. Are there equivalence classes of CFTs that can be coupled together, but then some other CFTs can't be coupled to anything in that class? That would suggest that maybe there are different non-perturbative theories of quantum gravity. If it's possible that any two CFTs are in the same class, that they can be coupled together, or there's some chain of CFTs where eventually I couple CFT1 to CFT2, that would sort of suggest maybe that all of these gravity theories should be part of the same theory. Okay, so we had that kind of general picture, and then the more specific claim was that if I had two CFTs that were in the same class that could be coupled non-trivially to each other, our results suggest that I could actually find a state of CFT2 that would be dual to a space-time containing an arbitrarily large region of this causal diamond in the space-time dual to a state of CFT1. Okay, so we choose a holographic state of CFT1, dual to some space-time. We think about this particular region, and then I defined this state of CFT2 using the Euclidean path integral, and argued that for small enough values of epsilon, the geometry dual to that state, if we choose everything correctly, actually has this property that there's a bubble inside this geometry, and inside the bubble, you have this region of your original space-time. Okay. So going back, I guess, to the original motivation suggested that, maybe the specific degrees of freedom and the specific Hamiltonian of the various holographic CFTs that we deal with perhaps is less important than we think. Maybe these different holographic CFTs are kind of dual to the different allowed asymptotically ADS behaviors for our for this larger theory of quantum gravity. But the full quantum gravity theory itself, or maybe the local dynamics of gravity in the bulk, maybe that is dual to something more universal that doesn't depend on the specific degrees of freedom or Hamiltonian of a CFT. Maybe this quantum gravity physics, the local physics in the bulk, has something to do with some universal physics, entanglement structure and dynamics, or something of that nature, that is present in any holographic CFT, or maybe any quantum field theory. Okay, so thank you.
Thanks, Mark, for that excellent talk. Maybe we can all unmute ourselves and clap. And maybe we can go to more questions. I have a couple of questions. I couldn't hear a bit of your talk in between, so I'm sorry if you already answered this. But you mentioned that one can look at the constraints that one would get by boundary bootstrap, by boundary CFT bootstrap. Did you actually use that anywhere? Did they impose any constraints on the results that you got on the kind of interfaces?
For me, I simply assumed that that I was talking about two CFTs that had some non-trivial coupling at an interface. So I haven't really used these properties. But yeah, I mean, one could imagine for example, one could ask the question, given two CFTs with specific central charges, what are the possible values of the boundary entropy?
Right.
That would kind of constrain our models. I was assuming that we could have any value of tension, say, within this interval that I was describing, but maybe there's some bootstrap kind of constraints that says log G should be within this range, and then that would further limit the range of tensions that we're allowed to use in our holographic model.
Right. You also had this result that if C2 was greater than C1, it seemed like you didn't have any restriction on G, but if C2 was less than C1, you had a restriction that log G should be large enough.
Yeah, that's right. So
right.
in this case, with a smaller central charge for C2, then we had to choose on the gravity side, we had to choose a bubble tension that was sufficiently large in order to get the topology of solution that we want. So this means that from the CFT perspective, it's not enough just to choose any interface between these two CFTs. We actually have to assume there's an interface that corresponds to a large enough boundary entropy.
Right. Okay.
I should say that there were some results. There were some results by Bacchus and collaborators recently that related to this they used a similar holographic model, and they understood that the interface tension in the holographic model was related to how easily the excitations can propagate from one CFT to another. So actually, for these large tensions, I believe that there's sort of a higher transmission coefficient, and so it's like the gravity theories are maybe more readily coupled. So from that point of view, it's not surprising that we would have the bubble solution that gives a faithful approximation for a larger tension, but maybe not for a smaller tension where the CFTs aren't coupled as strongly.
Right. Okay. Just maybe one more question. Sorry, I'll just ask one more question and maybe
please.
And I'll let go. Does your construction have anything to say about, there's these recent constructions where people have coupled some gravity theory to a region asymptotically with no gravity actually, but does your construction have something to say about the duals of such?
Yeah, let me say that. If you were quick, you would have seen me flip through a slide in 0.1 seconds. Okay, this slide. Okay, so Yeah, I'll just mention, one of the hot topics lately is the set of models that take a holographic CFT and then kind of, you imagine coupling it to some auxiliary quantum system that allows a black hole being described by this CFT to evaporate, even though normally it might be an asymptotically ADS spacetime and not evaporate. If you couple to an auxiliary system, then it can evaporate. And so people have studied the page curve by evaluating the entanglement entropy of this radiation system, and they find the expected behavior for a unitary theory. One of the very interesting features of this is that the entanglement wedge for this radiation system, it undergoes a transition at the turning point in the page curve, where after the turning point, the entanglement wedge for the radiation system seems to include a part of the interior of the black hole geometry. And so that's sort of fascinating because, we think of the entanglement wedge as being the dual of the density matrix describing this subsystem. And so, apparently, regardless of what radiation system you decide to use, maybe it's another holographic CFT, but maybe it's a bunch of, an Ising model or just a bunch of qubits. The argument kind of suggests that the entanglement wedge at a late enough time of this radiation system should include this black hole interior. Okay, so that kind of suggested that that maybe sort of very general quantum systems could somehow be holographic, be describing the interior. And I think that fits in with a theme of today's talk, where I'm suggesting that maybe indeed very general quantum systems could actually approximate states of systems that we think of as being more conventionally holographic. And I think, this last example gets at that very specifically, where I started with a system of two CFTs entangled with each other. And this is the standard dual of the two-sided black hole. But then I said, well, we could have a completely different CFT. And if I set up this path integral state, then now this is an entangled state of sort of two rather different systems, CFT1 and CFT2. And we understood the dual geometry of this could be, could be like this wormhole where, say, here's our black hole, and then behind the horizon of that, you have this interior, but actually, that connects on to a very different theory. So this is kind of an example where instead of a CFT and a radiation system, well, you could think of CFT1 as our original holographic CFT, CFT2 as our radiation system, and now here we have a mechanism for some say radiation system which is very different from CFT1 to still be describing a part of the interior of the black hole described by CFT1.
Right.
Right. Yeah.
Okay.
I guess
Thanks.
my question was going to be sort of what you already answered. I think in the phase where the upper part of the cylinder connects to the bottom, there should be. Have you studied entanglements of subregions in that phase? There should be some interesting structure to the RT surfaces of various subregions, sort of in the middle part. Like,
yeah. So I mean, this is one of the sort of further projects that I'm talking about with my student.
okay.
So far we haven't looked at subsystem entanglement entropies, but we're kind of currently investigating.
Yeah, I would think there will be interesting sort of quantum extremal surfaces of sort of part of one system encoding something you didn't think was encoding.
Yeah, indeed. I mean, this is what let me. So, well, even in this picture, you can see if I look at a large enough subsystem, then we'll have some extremal surface that crosses the interface, and so then you certainly have part of that interior.
I just want to point out, this sounds very similar to Juan Maldacena gave a talk at this meeting at CERN, which was organized by some the fuzzball community. And they had these wormholes that sort of connect the top and the bottom. like the pictures you're drawing, and they have some interesting applications to entanglement in cosmology, in cosmological settings. So I think that
this is
this work is
unpublished?
not published. Yeah,
Mm.
I think it's going to be published soon, but Juan gave a talk at, I think the video is online, you can find it.
I see.
It
At
was
CERN.
organized at CERN by the fuzzball community, and they talk
Okay, very
about this
good.
sort of state in which like sort of the top and the bottom of the geometry get connected, and it's very similar.
I see.
And they had some very interesting sort of, you know, these island type phenomena where you consider a subregion in what would be your middle region, and then it's sort of the thing that you are drawing as ADS-L1 sort of has some island that's sort of, you know, dual to that part. So anyway,
I
I
see.
just wanted to point that out.
Okay, very good. Thank you.
I think we have another question by Junik. Junik, if you can unmute your mic.
Actually, I'm audible now?
It's slightly broken. Maybe you can you try again?
Am I audible now?
Yeah, no, it's better.
Okay, thank you, sir. My question is actually quite a basic question. That is, likewise, here we are thinking of that CF2 is hiding kind of in the bubble or in the vacuum space of CFT1. Is there further CFTs which can be hiding inside them? Like, can there be a chain continuing?
So that it sounds. Sorry, what you said sounded a bit like this picture here. I mean, I can.
Yeah, right.
I can have CFT. So this was my construction if I had a CFT2 with significantly smaller central charge, and then I can try to draw. I think I can draw. Okay, so if I drew the dual of this thing of this state, then so I would have my my CFT2 asymptotic region, and then I would have a bubble inside associated with this CFT3, and then inside of that I would have a bubble
Of
associated with some other,
CFT5.
and then eventually in the middle, then I have the CFT1. So so this kind of construction exploits that picture that you mentioned with concentric bubbles in order to approximate a gravity theory with a much smaller cosmological constant with a CFT that has a small central charge.
Okay.
Hi, Mark.
Can we use any?
Sorry.
I heard Shiraz and someone else. But...
Actually having a second part in the question. Can I have it?
I'm sorry, I didn't hear.
Actually, I have a second question. Can I have it?
Okay, please.
Yeah, that is likewise here we are using a gravitational approach to find the other CFT. Is there other approaches that we can use?
Junik,
Yeah,
it seems like your audio is a little bad. Maybe you can just type your question in the chat and then I can read it out to Mark.
Good idea.
Hi,
Shiraz, do you want to ask your question in the meantime?
Yes. Mark, in the middle of the talk, you flashed a Lorentzian geometry corresponding to your path integral with 2 in the middle of 1. I somehow missed that. Could you
Okay.
that?
Okay, let me just get back to that. This one.
Yes. So now, where is the bound? I sort of can't understand this picture.
Okay,
where is the boundary of? Is there a Penrose diagram?
Yeah, it's like a Penrose diagram. So I'm suppressing the just take everything and multiply by a sphere. But so you can think of this in 3D. Just take this and then rotate it around the axis. And so that's the geometry inside of the bubble. It's like a a region of space, and then the bubble collapses. If you're living here, the bubble will collapse on top of you. And then from the exterior,
black is the boundary of ADS, and red is the domain wall.
Sorry, red is the domain wall. This is the center of ADS.
Yes.
Equals 0, and this is the boundary of ADS. Okay, so my CFT, so my CFT state, was a state at time equals 0.
Yes.
And then when I draw these pictures, I'm saying, let's just take that CFT and use the CFT2 Hamiltonian to define a state for all times. And then what is the geometry dual to that state? And so it's, from the point of CFT2, it's some high energy state. And so the geometry looks like an ADS Schwarzschild geometry, but then I have a bubble at some point, and the bubble can either at time equals 0, it could be outside the horizon and then fall in, or in other cases, it could actually be behind the horizon for all times. And so that would be the second case here. So the bubble always starts from the past singularity of Schwarzschild and ends up in the future singularity of Schwarzschild.
I see. And then this part of the spacetime is then matched with the path that is described by CFT1?
So in the Lorentzian picture, I mean the left, okay, this bubble here, inside that is, the inside of that is described by the semi-classical gravity theory that would be associated with CFT1.
Yes. Okay. Sorry, I'm sorry for being so slow, but in the two diagrams you've drawn a leftmost diagram and the second leftmost guy. So the second leftmost guy is has the gravity dual, the path that is naturally gravity dual to CFT2, right? And the leftmost guy is CFT1.
That's right. So so this part has no asymptotic boundary.
Yes.
So now, of course, we're talking about just a state of CFT2.
Yes.
CFT1 was only involved in preparing that state.
Right. And then if we drew the Penrose diagram for the full space-time, where there is a part of the asymptotic boundary in CFT1 and...
So that's only in the Euclidean continuation. So this picture only has an asymptotic boundary, which is associated with CFT2 for the entire cylinder.
I see. Thank you. Okay, thank you very much. Yes.
Sure. Did we get the typed question?
Yeah, we actually did. He asks, is there any other approach other than gravitational ones to detect the presence of the CFTs hiding inside?
I mean, I think from the CFT point of view, these states that I'm talking about are just, well-defined states. So let's go back to this picture. So I can certainly describe this state, given, even if the CFTs are not holographic. You take CFT1, you take CFT2, you choose some interface between those two, which is one of these things classified by the boundary bootstrap of the tensor product theory. And then I choose some parameter epsilon. And so that is some state of CFT2, even if this is the Ising model. And so you can always talk about these states of a state of one CFT, which is sort of constructed from another CFT using the Euclidean path integral. Those are just there in the Hilbert space of the various CFTs. And so then the only question is, the question is sort of a gravitational question. My question is, does this state of some holographic CFT2 constructed in this way have a bubble, and then inside the bubble, does it look like the dual of CFT1? So it is kind of a gravitational question. Now, okay, so I should say, okay, good. So let me expand on the question. So of course you could ask, which observables of CFT2 would you look at in order to realize that you have some part of CFT1 inside, or that that your state is somehow one of these bubble states. And so one of the, I'll draw again. So I already mentioned one thing. So let's choose different colors. So I could look at entanglement entropy. And so I would notice for this state, there can be some interesting behavior of the entanglement entropy because the RT surfaces for large enough regions could actually penetrate into the inside. Okay. If you were to do this for our simple model, you would actually find a phase transition in the entanglement entropy as I increase the size of my bubble. So if you could just, in the usual way, kind of try to reconstruct the geometry using entanglement entropy, then you would notice something funny. Even from the CFT perspective, you would notice an interesting behavior of the entanglement entropy. Now, you could also, another way to try to ask about the physics inside the bubble from the CFT perspective would be to consider some local operator. And so here you have an I think it's important to distinguish between these two cases where the bubble is either inside a black hole horizon or not inside a black hole horizon. Because if the bubble is not inside a black hole horizon, then you could actually have a local operator here, and this probably has a relatively simple description in terms of boundary operators that you could uncover using some HKLL type construction. So the HKLL here would involve a propagator that actually goes from the interior of the bubble to the brane, and then from the brane to the boundary. And if you could understand these propagators, then it should be possible to write the local bulk operator inside the bubble as some sort of smeared operator in CFT2. So you could even you could even study those sorts of operators in CFT2 to try to uncover local physics inside the bubble. If the bubble is completely behind a black hole horizon, then it's certainly more mysterious how to recover the local physics. These entangling surfaces actually can still penetrate the bubble even if it's behind a black hole horizon. But
there's one other question in the chat.
sure.
Akash asked, what's the physical significance of using the vacuum state of CFT1?
Yeah, so this was just my simple starting point that I decided the simplest thing I could try to approximate would be empty ADS space. Okay, so, but it's important that we have ADS space as a classical solution of some low energy theory with one particular cosmological constant, and now I'm trying to approximate that by a CFT that would normally be dual to gravity with a different cosmological constant, and possibly completely different fields and so forth as well. But then I emphasized a little bit later, so there's nothing particularly special about the vacuum state. I could take exactly the same operator defined using this Euclidean path integral. So exactly this operator, and apply it to any other state. And so, for example, where did it go? Yeah, I could look at states that I get by perturbing with sources, and the whole thing should work. So in this case, one could investigate just in the first case, if I add these sources, what does that do to the Euclidean geometry? This gives you some different boundary conditions for various scalar fields. For example, that'll give you a different Euclidean geometry, different Lorentzian geometry once you analytically continue. And then you can investigate, what is the Lorentzian geometry over here? And so I think, in fact, you can argue that even if you have sources, so even in this perturbed geometry, I think well, we argue in more detail in the paper that the interior of the bubble here, even though there are some fields now turned on, some scalar fields here that might have a non-trivial profile, we argue in the paper that in the inside of the bubble, you should still see those fields in approximately the same configuration. And basically the argument is that in the Euclidean picture, there's some kind of boundary to bulk propagator that takes your sources, and here I'm talking at the linearized level, it takes your sources and gives you some fields on the time equals 0 slice. In this picture, you could do a similar kind of perturbation theory, and at linear order, again, you have some boundary to bulk propagator. This will be affected by the presence of this interface brane, but the limit epsilon goes to 0, that interface brane goes out towards the asymptotic boundary, and one can argue that sort of the propagator that determines the map from the sources to the initial data, this should approach the propagator over here in the limit that epsilon goes to 0. So I think as long as you have a bubble, as long as you can approximate the vacuum state, then you can approximate any nearby state as well.
Hi, Mark, you have some sort of, the state in CFT2 has some energy.
Yes.
And that's presumably some function of your epsilon and g. Is that
yes.
right? And in the situation where your bubble of CFT1 comes outside the horizon of the black hole, presumably that only happens when the energy in CFT2 is high enough? No. I mean, is there some connection?
Yeah, I mean, let's see. Let me go to the...
I mean, the intuition is that you should, to be able to do such funny things, you probably need to be at high enough energies. I was wondering if you could make that precise.
Yeah, so I mean, I think, okay, we have, I don't think I have a nice formula to elucidate that immediately, but there is a short section of our paper. I kind of worked out what is the energy as a function of various parameters, that the size of the bubble. So the larger you generally get a higher energy, the smaller epsilon is. So as epsilon goes to 0, the energy goes to infinity. That doesn't necessarily mean the bubble comes outside of the horizon. Okay. So the bubble gets larger and larger. Oh, here we go. As epsilon goes to 0, the size of the bubble goes to infinity, but it can still be inside the horizon. So this phase diagram here is actually for the limit of very small epsilon. So you see that sometimes, even if the bubble becomes arbitrarily large, the black hole also becomes very large, and the bubble stays inside the horizon. In this case, the bubble is outside the horizon, regardless of how large it is. So whether the bubble is either inside or outside of the horizon seems to be determined more by this tension. I'm not sure I have a great understanding of it.
Yeah, right. Okay, but you say that the size of the region that you can well approximate goes larger and larger as epsilon, as the energy.
Yeah, that's right. As long as you can do it, then you can just take epsilon to 0, and then the region becomes arbitrarily large.
Okay.
Sometimes it's inside a horizon, sometimes it's outside a horizon.
Okay, thank you. And sorry, do all your states, you were working in ADS3, say we're working with the NS-NS boundary conditions. Are all your states always with energies above the BTZ black hole creation energy?
Yeah, I mean, I'm kind of focusing on this limit of small epsilon. Okay. So we probably at somewhere we have some code that includes the lower energies as well. But I think I mostly ignored that case.
But could you get such funny stuff at energies smaller than the black hole energy? Could you get these bubbles also at energies smaller than?
Yeah, I don't remember if they're ever. Okay, I can't remember if there's some situation where you actually find a bubble and and the energy is below that. I suspect no. I can't remember specifically if we ruled it out.
Okay, thank you.
Do we have any more questions for Mark? If not, let me thank Mark again. Thanks, Mark, for taking the time out and giving this nice talk to us.
Sure. And thanks again for waking up early.
Wonderful talk.
Thanks.
Okay.
Okay, see you.
See you.
Bye.
Yeah, if anyone has additional questions, I'm also happy to hang around for a few minutes.